In this video, we're going to go over how to run parallel jobs on the cluster. I'm going to be using Triton in this video, but this should work on the Pegasus cluster as well. So I'm just going to navigate to my Scratch space to this MPI test folder. So what is a parallel job? So we know that a serial job is when we assign a single core to work on each one of the tasks in our program. It runs in serial, does things one at a time. Parallel job, conversely, is when you assign multiple cores to perform tasks at the same time, so it gets done, faster than a serial job. It's done in parallel. Usually, when you're running a parallel job, you would request multiple cores right here where it says b sub -n. In this case, I'm requesting 12 cores. When you're using multiple cores, it's considered parallel computing. Now, it's important to note that your code, the code itself, whether it's a Python program, an R script, needs to be designed to run in parallel. Okay, you can't just assign, you can't just request 12 cores in your job script and then expect the job to just run in parallel. So your code itself has to be designed to run in parallel. I think there's some packages that can do that, like in R, I think it's called Parallel or something like that. Python, you can find the package probably through online sources, but there's different means to do it. A lot of people will use software called MPI, which is called Message Passing Interface. Essentially, MPI is used for parallel computing. It's a framework, and it allows different processes either on the same machine or like multiple machines to communicate with one another. So it allows the cores that are working on the tasks to communicate with one another. That's why we use MPI. Here, I'm just loading Spectrum MPI, and that's what we're going to use with this example. But let me go over some of the other parameters here. So we said that we're using 12 cores for this job. This is a new parameter. We didn't use this in the serial job video. It's b sub r span p tile equals 4. And how this reads is we want to use 4 cores per node. So if I'm requesting 12 cores in total, and I'm requesting 4 cores per node, I'm gonna get 3 compute nodes working on my job. You don't have to have this parameter to make a job parallel either. This just makes it distributed because you're using multiple nodes, but you could use all 12 cores on a single compute node, and it's also considered parallel, so long as your program that you've designed runs in parallel as well. So we've requested the cores, we're requesting multiple nodes, we're loading the Spectrum MPI module, and then we're running MPI run, followed by the number of cores I'm requesting, 12, and then we're executing this MPI hello world program. Let me go ahead and show you what that source code looks like. Essentially, I'm calling this the MPI header libraries. I'm retrieving some variables, specifically the processor name, world rank, and world size, or like how it will show in the output is hello world from processor, and then the name of the machine that's running the compute node that's running the process, and then the rank of that process, which is going to be 1 out of 20, and then out of the total number of processors, 1 out of 12, because we're requesting 12 cores in this case, out of the number of processors, which would be 12. It'll make a lot more sense once I run the job and you can see the output. So let's go ahead and, without further ado, submit that. Okay. So as you see here now, it's running, and you see 3 execution hosts. These are my 3 compute nodes that I said I wanted to request, and 4 cores per node to a total of 12. 4 tasks are being assigned to T031, another 4 are going to T036, and another 4 are going to T30. So 4 tasks are being done on each node at the same time to get this done faster. It's just a very basic example of what parallel computing looks like. I'll make sure that it's done. Okay, no unfinished jobs found. I'm going to clear my screen. All right, so let's take a look at the output. So you see here 4 on T031, 4 on T036, 4 on T030. Okay, so only 3 nodes, that's right. This is what the job looks like, some memory usage summary, and then this is what we wanted to see. So you have hello world from processor on the machine T031. This is rank 0 out of 12. So it always starts with 0, by the way. That's just how the ranks work. This is rank 0 of 12 processes. Then on the second one, which is number 1, T31, 1 out of 12, T31, 2 out of 12, T31, 3 out of 12. So you see it's doing the 4 ranks, the 4 processes on T031. And at the same time, it hops over to T036, which does rank 4, and then rank 5, rank 6, rank 7, and then so on and so forth until all 12 are used. So you can see that multiple tasks are being assigned to cores on different nodes, and they're working together at the same time to resolve that issue. So that's just a very basic example of how parallel jobs would work. The main things to note, once you've designed your code to run in parallel, is the parameters you want to set, I suppose. You can still use the normal queue, just like a serial job, and then you would request multiple cores for your parallel code here. And then you want to make sure that you're essentially requesting what you need to in your source code. You have to make sure that it runs in parallel. You can't create just a random serial R job and then assign it 12 cores and then expect it to use 12 cores, because it won't. We have more information about running these parallel jobs in our documentation, which I will share in the URL in the description of the video.